All right, let's find some more limits, shall we? All right. You know, we haven't talked about converge and diverge, but let's talk about that a little bit more here. Here's example 2a. I want to have a sub n is equal to n to the 3/2 power over n to the 3/2 plus 1. You are finding a limit. Yes, do I absolutely believe you can look at this and tell me the answer because in your head you find the limit. However, you have to write limit notation. A limit is an operation. So in order for you to tell me that this answer, n to the 3/2 plus 1, is equal to 1, it's 1 because you took the limit, right? So you have to have this. You have to have limit notation. In order to get to that answer, you have to have your limit notation. All right? Okay. Now, look at what happens here. Let's go purple. What if I have b sub n is equal to -1 to the n of n to the 3/2 over n to the 3/2 plus 1? It looks like an H. So the only thing that I'm changing here is I'm putting that -1 in there. What's that going to do for me? If I take the limit as n approaches infinity, -1 to the n to the 3/2 over n to the 3/2 plus 1. What happens if I have a even number? Yeah, so when I have an even number, my exponent here is going to make this positive. What happens when I have an odd number? Yes, so my exponent here is going to make it negative. Other than that, oopsie daisy, my coefficients are still 1, right? The only thing that's changing here with this limit is it's either going to positive or -1. If it's even, then my limit as n approaches infinity of my sequence is going to be a positive. If it's odd, then my limit is going to be negative. All right? So, if I'm looking at this, am I going to a specific value on A? Yes. Am I going to one specific value on B? No. So if I talk in terms of converging and diverging, A is going to what? Converge. Good, because it goes to a specific number. Remember we talked about that in the last section. If it doesn't go to, my limit doesn't go to a specific number, then what is that? Yes, it diverges. Good. I have our graphs here, so I want you to see what that looks like. So here, my sequence goes to one specific number, right? I'm taking my sequence and it is bounded. That's another bounded right here, and it converges. Bounded above because it's up on top. Here, this is a bounded sequence because it's going above and below, right? So it's bounded on the top and the bottom. But it also diverges because I've got this back and forth, back and forth, back and forth stuff. Something I want to point out to you now, which make an impact when we talk about alternating sequence or series also, is the alternating -1 to the n part of it that I'm looking at here can make an impact. So watch that alternating sequence. Notice what happens here. It messes with our positive and negative, so you just have to pay attention to that. That's the moral of that story. Okay. Cool. Cool, cool. All right. So let's do another review here of Calc 1 limits. Squeeze theorem. Remember that one? Ooh, it's so good, isn't it? We're going to do the squeeze theorem for sequences. And guess what? It's the same thing. Whatever you do with limits, the same thing applies when you're talking about limits with sequences. All right, let's write it out though, because I think it's good to write this out so you can have all the information. All right, so here is our definition. We're going to let my sequence here, A sub n, and it's a good refresher because in case we forget what the squeeze theorem was. So I have 3, A, B, and C. Those are squiggly brackets, by the way. I'm just mediocre at making them. B sequences with this order. A sub n is less than or equal to B sub n, which is less than or equal to C sub n. For all integers n that is greater than some index capital N, if the limit as n approaches infinity here of A sub n equals the limit as n approaches infinity of C sub n, which equals some value L, then the limit as n approaches infinity of B sub n also equals L. All right, it's a video, so pause and write that down if you need to, because here this was what's happening. Your small sequence and your big sequence. So this is set up to begin with. B's in the middle, A is smaller, C is bigger. That's just known, all right? That's a fact. So if I take my limit of the big one, the small one, and the limit of the big one, and they give you the same value, then you are squeezing the middle one. If the top and the bottom, oops, I said that backwards. The top and the bottom have the same value, then the middle also has to have that same value. You're squeezing to the middle, right? And so a lot of times whenever you do squeeze theorem, we have trig involved where you can have those top and bottom bounds. So check this out. I'm going to scoot this up a little. Here's example 4. Find the limit of B sub n is equal to the cosine of n over n squared plus 1. Okay. Whenever I go to find this limit as n approaches infinity here of the cosine of n over n squared plus 1. This is going to be infinity over infinity, right? But if I try to do L'Hopital, my cosine is going to turn into sine, which will always be infinity over infinity, infinity over infinity, infinity over infinity, over and over, right? Okay, so if I have this value and you have this trig in the numerator, remember what happens with cosine? Oopsie daisy. Let's come over here and go red on it. Cosine starts up and goes down. So what does it go between over and over? 1 and negative 1, right? It's bounded between 1 and negative 1. So I know that cosine has to be stuck between 1 and negative 1. So negative 1 over this n squared plus 1, let me scoot this little fella down, it's our graph, which is less than or equal to cosine of n over n squared plus 1, which is less than or equal to 1 over n squared plus 1. As long as you have that same denominator, you're good. We know cosine bounces back and forth between negative 1 and 1, but if I have that same denominator, then I'm making the same comparison. That's the key. All right? Okay. Then I take my limit of the lower one as it approaches infinity. We know that's 0 because the denominator grows huge, right? Take the top one. We know that also goes to 0 because the denominator gets huge, right? Therefore, by the squeeze theorem, the limit as n approaches infinity of cosine of n over n squared plus 1 also equals 0. All right? So when we use the squeeze theorem, there's some There's some criteria, that needs to happen. You need to have your limit notation. You need to set up your inequality. You need to take the limit of the top and the bottom, showing this. All this can be done in your head, and I get that, but this is a proof. Squeeze theorem is a proof. And the reason that you have the therefore statement at the end is because you're proving how this works. By these steps, that's how I can give you what my limit is, because the squeeze theorem dictates that, right? So you have to say, therefore, remember these 3 dots means therefore. It's the end of a proof. That's how you write it. Therefore, that's my final solution that comes up with it. And look at the graph that goes with this, right? Red is A sub n, it's coming in. Blue is B sub n, and then, or pardon me, C. And B is what squiggles right in there between that. But it's much easier to look at this one and this one, and so then B has to squiggle in between there and also go to 0. Do you see that? Pretty cool, right? Yeah, it is. Because A is smaller, C is bigger, so B is squeezed in between them. Cool. Squeeze theorem. So you have to have those criteria for squeeze theorem just because it's a proof. But it's not too bad. And you do that with your trig a lot of times. When your trig bounces back and forth between something, that's when the squeeze theorem is helpful. All right, guys. See, it wasn't so bad. Do some limits. Learn it. Love it. You got this.